stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job, to redefine what is possible. My name is Ivan Amato, and I am your DARPA host, and I'm pleased to have with me in the studio today Troy Olsson, a program manager since 2014 in DARPA's Microsystems Technology Office. Troy earned a pair of bachelor's degrees, one in electrical engineering and one in computer engineering, from West Virginia University, and a master's and doctoral degree in electrical engineering from the University of Michigan. For a decade prior to coming to DARPA, Troy founded and led a series of programs within the Micro-Electromechanical Systems Technology Department of Sandia National Laboratories in Albuquerque, New Mexico. Thanks, Troy, for joining me in the studio today.
No, it's a pleasure to be here.
So I'd like to start out our discussion with some background about you. I'd like you to tell me about your education, if there were teachers that were important to you as you were growing up and that led you in the kind of engineering direction that you have taken.
Yeah, sure. So I grew up in a small town in West Virginia, Weston, West Virginia, to be exact. When I was in high school, I had exhausted the math classes that were available at my local high school, so I ended up going part-time to West Virginia Wesleyan College, and they set up kind of a class for many students from my high school to go do that, a class for high school students at the local college. And before that, I'd always been good at math, but I never really knew how to apply it. I figured I would go into medicine or something of that nature. And as part of that special class they set up for us, the first half hour, Professor McBride would come in, and he was an engineering physicist, and he would come in and relate all of the calculus we were learning to physics problems. And I just found that fascinating. So that happened when I was a junior in high school, and from that point forward, I wanted to be an engineer.
So I'd like to hear a little bit about the phase of your career where you really worked a lot on MEMS, and again, that stands for Micro-Electromechanical Systems. I know you did that even before going to Sandia, so talk a little bit about that whole MEMS part of your work.
In graduate school at the University of Michigan, I worked for Professor Ken Wise, who's one of the founders of MEMS. There I worked on analog interfaces for neural recording electrodes. So I was developing integrated circuits to be able to record neural action potentials from the brain for doing things like restoring function to people who have nervous system disabilities like paralysis. Could be other things in the stimulation sense like blindness or hearing loss or other things of that nature. I then went to Sandia National Laboratories where I switched things a little bit. At Michigan, I was designing circuit interfaces for MEMS, and at Sandia, I started actually designing the MEMS components myself and led a team of people designing and implementing those. Primarily, we were working on small acoustic devices. So you may not know that in your phone, an RF signal is immediately converted into an acoustic signal.
And RF, by RF, you mean radio frequency signal?
That's correct, sorry. Yes, I mean radio frequency. The radio frequency signal, which has a really long wavelength, is converted into a acoustic signal, which has a very small wavelength, which allows you to filter it in a small form factor before it's turned back into an electrical signal. And so I was working on technologies that do that function, but more for Department of Defense applications rather than cellular phones. Also worked on other things that were really at the interface of vibrational systems and acoustic systems and electronic systems.
All right, and then what was the pathway from Sandia to DARPA?
I was a performer doing a lot of the research on those small acoustic wireless components. Bill Chappell, the current director of the Microsystems Technology Office, was my program manager, and so when he was promoted, he called me out of the blue one day, I think that was in March of 2014, and said, "Hey Troy, this is Bill Chappell. How would you like to come to DARPA and be a program manager? I think you'd be great at it." And I shared an office with somebody, so that was kind of a strange conversation. I said, yeah, that sounds like a great opportunity. Can I call you back in a few minutes?
And that's all it took for you, just a few minutes, and then you knew what your decision would be?
Oh, of course. Yeah, I mean, after that, anybody who gets an opportunity to come to DARPA, it's a fantastic opportunity. Of course, I had to come interview and put together a talk that outlined the programs I would start. I had to come interview with the office director, but how it all started was from a phone call from Bill Chappell.
Speaking about those programs, we're going to dive into talking about a number of those. You have a very large portfolio, larger than most program managers, so we'll only talk about a few. But there are two questions I want to ask you before we do that. And one has to do with your name, Troy. I call you Troy, but your official name is Roy. And I'm just wondering if you could tell us the story of your name.
Yeah, so my official name is Roy Harold Olsson III. Turns out my dad really wanted me to be named after him. He is clearly Roy Harold Olsson Jr. And my mom wasn't the biggest fan of the name Roy, so they made a deal that I could be named Roy Harold Olsson III and everyone would call me Troy. And apparently I reinforced this when I was a small child. As legend has it, I would sit in my high chair, and if people called me Roy, I would throw green beans at them and pound on the high chair, telling them that my name was Troy.
All right, nothing like negative reinforcement. So let's now move on to just some of your programs. Two that I think are associated with one another, we can talk about them together, go by the short names of Icarus and Vapor. Icarus stands for Inbound Controlled Air Releasable Unrecoverable Systems, and VAPOR stands for Vanishing Programmable Resources. I know that VAPOR came before Icarus, so why don't you tell us a little bit about the VAPOR Icarus story, which is an ongoing one?
Yeah, so in the Department of Defense, a lot of times we have problems with electronic leave-behinds. We don't want to leave things on the battlefield where other people might collect them. So we came up with the VAPOR program, which is a vanishing microelectronics program. It's designed to be able to make microelectronics that have reliability and performance commensurate with commercial off-the-shelf electronic components that don't vanish, but that when we want them to can rapidly vanish and be invisible to the naked eye.
Okay, and do you mean, when you say vanish, most people just think of poof, it's gone. Talk to me a little bit about the kind of technical pathway some of your performers, which is to say the research groups who have been working on this, the kinds of pathways they're taking to try to realize this idea of vanishability of materials.
Yeah, so there's really two approaches that have been really prominent in the VAPOR program. One was developed by the Palo Alto Research Center, PARC, and it is a vanishing glass substrate that basically turns into dust-like particles. And that glass can be bonded to integrated circuits and other things and cause an entire system to vanish. And by dust-like particles, the particles are on order size of 100 microns, which is about the width of a human hair. So those ones vanish to the naked eye, but the material itself doesn't, physically completely vanish. We did develop a material that does that. There was work done there at the University of Illinois and Georgia Tech and Cornell. Many of those materials work in a way where they're thermally unstable at room temperature. They'd like to be a monomer or basically be a gas. So we actually make them at very cold temperatures, say like minus 50 degrees C. In these cases, these vanishing materials are polymers, and we'd like to make a really long polymer chain to get high molecular weight, makes the polymer really tough. And then we link it in a certain way at the very cold temperature so that when we raise it up in temperature, it remains stable. Then in that material, we'll embed something that's called either a photoacid generator or a thermal acid generator, and that works just like you might expect it does.
It's like a trigger.
When you expose it to a certain wavelength of light, a photoacid generator creates an acid. If you take the thermal acid generator and exceed a certain temperature, it also creates an acid. That acid can break one of the bonds between the polymer chains. And at that point, then it becomes thermally unstable at room temperature again, and the rest of it just vanishes. And by vanishes, it turns from a solid directly into a gas. And so it just vanishes right before your eyes. The first time you see it, it's truly amazing. Actually, the second time you see it, it's truly amazing. And every time you see it.
And it really is amazing and clever chemistry to bring into the capability of vanishing materials. And this the program was successful enough in your eyes that you created a follow-on program, right?
That's correct. So we were brainstorming one day, what else beyond microelectronics could we do with these materials? We were thinking, where else could we push this material space? What else would lead to new fundamental discovery and developments, and could be also at the same time useful to the Department of Defense. And we came up with the idea of vanishing air delivery vehicles for being able to deliver things in a very precise way into difficult to reach locations, and then not having a leave behind that could either destroy the environment or lead to detection of the delivery. And so the Icarus program was born, and that program is currently in phase 1 and is developing vanishing air delivery platforms in a 2-phase program.
Right. And I know one of the exciting potential applications for these kinds of vehicles would be in sort of public health disasters, disease outbreaks. Tell us a little bit about those kinds of humanitarian applications that you have in mind.
Absolutely. So one of the first things when we started brainstorming about the idea, Matt Hepburn, who's a program manager, started interacting with me, introducing me to the idea of being able to deliver medical supplies using this technology and how exciting that would be. Thinking about things where there's been a humanitarian disaster and the runways are destroyed, roads are impassable. How can I get really critical supplies, vaccines, blood, medications, water, to locations that need it, where it needs to be precisely delivered, and do that in kind of, in some cases, a massive response without having to worry about going and collecting all of these air delivery vehicles? How do I get not only the thing to biodegrade and disappear back into the environment, but how do I make the cost low enough that you can basically have a glider that you don't care if you ever go retrieve it?
This is an exciting time in the life cycle of the program, right? Because I know that in the coming months, you're going to move outside of the glimmer in the eye and fundamental laboratory work, but toward vehicle tests, correct?
That's correct. So we have 2 things that are going to be coming up that will conclude phase 1 of the program. One is a flight test launching from 35,000 feet, showing a range of 150 kilometers and landing with 10 meters of accuracy, and doing that with a material surrogate. So the glider is made out of a material that has as exact as possible the same material properties as the vanishing material and the same manufacturing processes. So we're trying to test out, can we actually meet these flight profiles using something within the constraints of the material properties and manufacturing of a vanishing material. At the same time, we're also building a non-flying demonstration of the vanishing material. For example, we might build, not instead of a full airplane, just the wing of an airplane, but build that out of the vanishing material and show that we can actually construct a significantly complex structure from the vanishing materials. And then 1 year after those flight tests, we will do a flight test of the actual vanishing air delivery vehicle.
All right. Well, I will be excited to keep track of that, and we'll applaud with you when we see our first vehicle do a job and then poof, disappear. I want to move to another program. This one goes by the name N0, which kind of connects in with our ever more sensor-laden world. And so tell us a little bit about N0.
Yeah, so N0 is a program that's designed to basically take the Internet of Things and move it right to the tactical edge. So today when we think about the Internet of Things, it can't be what we really want it to be. We can think about applying it to our refrigerator or our toaster, maybe our car, but we're really limited to things that either can be plugged into the wall or that a human can take and plug in the device, every day or every couple days to recharge the battery. And that's because the energy efficiency of our electronics operating off of small, cheap batteries today is not high enough to sit there and monitor the environment all the time and report back things that it sees. So what we're trying to do in N0 is take kind of a new paradigm where we actually look at a very low power level. So near zero power to me means less than 10 nanowatts. And I chose that value because that's the leakage of a small coin cell battery. What we want to do is be able to sit there, continuously monitor the environment, looking for an event that we are specifically tuned to that doesn't happen very often but can't be missed. and then be able to wake up these higher power consuming electronics when we see that event. So you can imagine what kind of events could those be. Those could be like augmenting bridges and infrastructure with these types of sensors, looking for specific failure modes, earthquakes. You could imagine putting these throughout the environment. We're thinking about augmenting vehicles to be able to look for and find engine failures earlier. You could imagine dispersing them in the environment and detecting things like forest fires or chemical leaks or other things of that nature. And we have a whole class of these types of sensors looking for acoustic, vibrational, infrared, chemical, and RF, all being developed, all that can sense these very specific profiles, reject background interference, and consume less than 10 nanowatts. So they basically sit there always active, always listening, but consume basically standby type power consumption.
Right. Fascinating to think about sort of the world becoming, innervated with all kinds of sensors, almost the way our bodies are. I want to move on now to just one more program. This goes by the name AMEBA. That's spelled AMEBA. And the long form of that is a mechanically based antenna, and I'm particularly interested in this because I think it reveals sort of the way you apply your engineer's mind to this invisible world of radio frequency signals that's all around us. So talk to us a little bit about AMEBA.
Okay, sure. So AMEBA kind of comes from my love of looking at problems and thinking about the ways we solve them today and how those are insufficient. And if we could just do it this other way, it would be so much better, but we have some technology that's standing in our way of doing that. So in AMEBA, what we're trying to do is be able to communicate from really difficult environments, say like underground or underwater or over very long distances without some type of repeater network. And
I should point out, right, through ground and through water, radio signals do not travel very well through those media.
I would say high-frequency radio signals don't travel very well through those media. And the key then is to operate at low frequencies. And that presents a very significant challenge, is that the wavelength at low frequencies is extremely long. And in fact, that's the reason that they propagate well through water and ground, is because the wavelength is very long. And that allows the signal, because of the physics, to be able to propagate through those media over much larger dimensions. So the way we build antennas today, we basically push current through wires, either kind of straight wires to build things like electric dipole antennas or through coils and other things. And it's very, very difficult to produce a significant amount of, in our case, magnetic field when the antenna is very electrically small. That means small with respect to the wavelength using those techniques. Those techniques are fabulous at higher frequencies, but when you get to very low frequencies where you want to make something that in our case would be man-portable, it seems nearly impossible to make an antenna with any type of efficiency at those size scales.
Right.
And frequencies.
The military does have some antenna systems that can operate in these low frequencies, but they're enormous.
Yes, they're either the size of whole islands or counties, or sometimes they traverse states to communicate in these bands. In other cases, you might reel a very long wire that's a kilometer in length out of an airplane to communicate at these frequencies. But in any case, the dimensions are very, very large.
So it's going to take a lot of interesting physics to go from something of that size to a man-portable technology that will generate the same long wavelengths.
That's correct. And so our insight was that when we're pushing those currents through those wires, what we're doing is we're creating electric and magnetic fields, and we're expending energy to create them. And then, of course, we do that at a specific rate to determine the frequency. And what we did was we looked and said, well, what if we just started with something that actually had a high amount of stored magnetic field, for example, like a permanent magnet? And instead of then using our power to create that magnetic field, we would take advantage of what nature has given us, which is this permanent magnet. Of course, we've created it and machined it, but it's a natural material phenomenon. And instead, we created the RF frequency by moving it. And then we also had the insight that moving things mechanically becomes very efficient the lower in frequency you go. So while a mechanical-based antenna may be completely inappropriate, where your iPhone operates at gigahertz frequencies, it's in fact very appropriate at a kilohertz type frequency to take a magnet and spin it or mechanically move it to create an oscillating magnetic field. Of course, magnets aren't the only things that we're looking at. There are other types of materials that store these types of permanent fields. Electrets store electric dipoles, and there are other types of materials that we'll be looking at in the program as well. Another insight that we had was that if we actually just took one really big thing and tried to move it, that the amount of stored mechanical energy there would be very high, and that also would lead to a lot of inefficiencies. So one of the really key ideas of the AMEBA program is, can we break that large thing up into a number of small synchronized things that lowers the total stored energy and lowers the power consumption? And the risk that we're trying to mitigate is, how small a pieces can we break it into before the interactions between the pieces, particularly the magnetic and electric interactions between them, start to dominate the overall system performance? You can imagine two magnets that are close together, have a lot of force between them, they interact with one another, so trying to manage and control those interactions is the big risky part of the program that we're trying to overcome here at DARPA.
Okay, and if you get utopian and you imagine this program being as successful as you want it to be, give us a sense of what additional communications capabilities it would offer us.
Yeah, so this is a low-frequency transmitter, so you're thinking about things like voice and text. So at these types of frequencies, it's not really possible to do things like video, for example. But it would give you a new capability, say from underground, if you were a miner, to be able to text or do voice to somebody above ground. So if there were something like a mining accident, you could tell somebody where you were at, and you would have that type of communications. Similarly, from underwater, maybe 50 to 100 meters underwater, one could communicate text from underwater to the surface, or to something even flying overhead, which today isn't just not really possible.
And there's one other application that's quite interesting to me, and that's the way these low frequencies can travel through the atmosphere in unusual ways, so that it potentially could enable very long distance communication between 2 points.
That's correct. So at a slightly higher frequency, say around 10 kilohertz, there's a waveguide that's formed between the ionosphere and the surface of the Earth. We often use that waveguide to bounce signals off of in what's called the high-frequency band. So things like ham radios work based on that physics. But you have to know the location of the receiver to know how to bounce it down to the receiver. So if you don't know that, you'd much rather fill that waveguide with the RF, and that's what happens at, say, 10 kilohertz. So we're trying to build something that can actually couple to that waveguide, and once you couple to that waveguide, the propagation physics, or the loss of the RF as it travels over distance, is very favorable compared to things that don't propagate in the waveguide. And so that's what would enable you to reach these really long-range communications, thinking things again like voice and text over hundreds of kilometers from something that you can really hold in the palm of your hand. Just not possible today using other technologies.
We've talked about 4 different programs, and when I think about all the different technical components of them, it's rather amazing. So this makes me, realize that your engineer's mind really covers a lot of territory. I think we once had a discussion where you were telling me that in some ways you think the task of the engineer is quite a creative one, that there's really kind of a connection between the kind of problem-solving engineers do and the creativity that we might even see in artists. I'm just wondering if you've got some thoughts about that and how you might compare and contrast those kinds of ways of exercising our minds.
Yeah, so that's actually an idea that I borrowed from my thesis advisor, Ken Wise, who at the University of Michigan on their North Campus, they have centrally located art, music, engineering, and I believe architecture. And his point was, they basically stuck all of the creative fields together. This is, some people might not think that music and engineering would go together, but I think that was his insight, that becoming an engineer and being an engineer requires quite a bit of creativity. And I think particularly if you want to make anything more than an incremental improvement to the way things are done today, it really requires the type of creativity to look at the way that they're done, understand the limitations of that, and then come up with some completely new approach that would allow you to get beyond those limitations and make the 10x, 100x jumps in performance that we're all seeking, particularly here at DARPA. So creativity, I think, is a huge part of being able to found new programs, particularly in areas that are not obvious, that aren't leading like from one program to another. Hey, how do I get off this certain trajectory and get myself on a different trajectory, which is the one I want to be on? And I think it's really the creativity that allows you to make that kind of jump.
Before we close, Troy, I'm just wondering if there is a science fiction technology, a technology that you might have learned about when you were a kid. You might have read a great science fiction book. You saw something in a movie. You came up with this idea yourself that does not exist now, but that you really think ought to.
Well, absolutely. I think both come from Back to the Future. So I am actually optimistic that one day I might get a hover car. And I would love to be able to do time travel. So I'm not so optimistic about that one, but you never know.
Well, and if you could do time travel, would you be more interested in going back or forward in time?
I would definitely be more interested in going forward in time and seeing what happens.
I knew you were going to say that. This has been absolutely amazing. We've gone from vanishing materials and vanishing vehicles to sensors that use almost no energy at all but are paying attention to the environment. We've talked about hover vehicles. So this has just been an amazing conversation for me. And I want to thank you, Troy, for spending this time with me.
Oh, thanks, Ivan. I really enjoyed it.
And thank you, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. For more information about Troy Olsson, his programs, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download this podcast and all the others, go to the Voices from DARPA page on DARPA's website.